Hi everyone, and welcome to the 10th webinar in the AWC3's webinar series about watercourse crossings. My name is Daniel Monaco, and I'll be acting as your host for today's webinar. Before getting into today's webinar, I just wanted to give everyone a brief introduction to AWC3 in case this is the first that you're hearing about us. So AWC3 is the Alberta Watercourse Crossing Collaborative. It's a not-for-profit organization whose primary objective is to facilitate information transfer around the issue of watercourse crossings in Alberta and their impact on native fish species. So that's what this webinar series is all about, is sharing that information from subject matter experts and trying to get it to as many people as possible. So since we have received some questions about this, I want to let everybody know that this webinar can be used for continuing competency credits for professional associations. So it counts for a half hour of credits and has been approved by most major professional associations. So if that's something you're hoping to take advantage of, please keep your receipts and your registration confirmation emails. And then, if you have any questions about that, you can email us at info@awccc.ca. So today's webinar is about engineering considerations for watercourse crossings, and we have Michael Bender from Millennium EMS Solutions as our presenter. So I'll give a little bit of a background on Michael Bender. So he's an engineer with more than 25 years of experience as a water resources engineer. Most of his experience has been in Alberta. He's worked on various culvert designs and tools for watercourse crossings and has worked in most parts of the province for either road crossing development or pipeline development. Michael has a PhD in civil engineering from the University of Manitoba, and he is currently a consultant at Millennium EMS Solutions in Calgary. So before passing things off to Michael, if anyone has questions throughout the presentations, you can submit those through the GoToWebinar toolbar on the right-hand side of your screen. I will be compiling the questions throughout the presentation, and we will get to those once the presentation is done. So the way this is planned to go is about 25 to 30 minutes of presentation, starting shortly, and followed by about a half hour of Q&A period. So any questions that are asked throughout the presentation, we do ask that it pertains directly to the topic of the presentation so that our presenter and panelists can answer those to the best of their ability. So without any further ado, I will pass things off to Michael.
Thank you, Daniel. Hello, everybody. Thank you for tuning in to listen to me. Today's topic resonates with me because I've been lucky enough to associate with a lot of key people over the years on the topic of watercourse crossings. They include people like Rich McCleary, Rick Bonner, Peter Denny, Kelsey Cure. A lot of the work we did in the late 90s is still relevant today. West Fraser still uses a version of the watercourse crossing tools we developed back in 1998. And I see lots of research going on today that builds on the tools we explored 20 years ago. Things like predicting road sediment and estimating habitat upstream of culverts based on available data. There's a lot of exciting stuff going on. This presentation is focused on basic engineering topics and on the thinking process about your options. From that perspective, I hope you consider repairing culverts before jumping to the conclusion that they should be replaced, because repairs are usually cheaper. And I hope you don't give up completely on round CSB culverts because they are very durable. In general, if you started this presentation as a biologist, you won't be an engineer at the end of the presentation. If you're an engineer, I'm probably missing all the technical bits that you love so dearly. If you're a regulator, please excuse the practitioner's interpretations. If you're a vendor with an innovative type of crossing structure, I hope you are giving a separate presentation because I really like some of the newer products nowadays. Regulatory references. I'm going to skip through a lot of this, or at least just skim through it, because Michael Hunka gave a presentation on Tuesday about this. So I don't want to repeat that. I'll just hit a few of the highlights. Related to watercourse crossings, you have the Fisheries Act, you have the Water Act, you have the Public Lands Act. And related to the Water Act, you have the Code of Practice for Watercourse Crossings and the Roadway Watercourse Crossing Directive. And the Crossing Directive is the piece that motivated a lot of a lot of the work that we're doing on watercourse crossings nowadays. Some of the other tools that you need in your pocket are the design guidelines for bridge-sized culverts by Alberta Transportation, and the companion document to that, which is the Fish Habitat Manual. Some of the highlights that I want to touch on, in addition to what Michael said on Tuesday, is that if you're building a watercourse crossing based on the code of practice, you need a QACE sign off on that. QACE is a qualified aquatic environmental specialist or fish biologist, and you need an engineer and owner sign off on that. So either an engineer stamp or an owner's signature. There's also a third option for an engineering technical specialist, in addition to engineer and owner, and that's it does give some flexibility to someone other than the engineer to sign off. If you build a culvert or do work related to watercourse crossings under the code of practice, you have to issue a 14-day notification. I think Michael covered that. Another key item is maintenance work. If the maintenance work is within 20 meters of the road, that makes your life easier as well. Activity restrictions, Michael touched on this on Tuesday. They're based on water body class, and you either have restricted activity periods to certain times of the year and different crossing types that you're allowed to build. Class A streams are the most sensitive, and Class D streams are the least sensitive. Clear span or open bottom structures or type 1 structures can be built anywhere in any of those types of crossings. Crossings that are not clear span but have in-stream abutments and are still open bottom, those are type 2 crossings. You can build those on unmapped Class B streams or Class C or D streams, the same as closed bottom types. But you may be required to justify those choices by saying that the type 1 is not feasible or not practical. Ford crossings. Ford crossings are not culverts or bridges. The ford crossing is when you drive through the creek and it's designed, the crossing is designed for that. Those are allowed on Class C and D streams. So after you have culvert inspection results, you probably have a culvert inventory, and you have probably prioritized your culverts. What's next? The inspections identify measurable things such as high velocity, hanging culverts. Hanging culverts are especially easy to identify when you have a waterfall at the outlet, and those are pretty easy to pick off during an inspection. Frequent washouts is an indication that your culvert is undersized. And if you have a history of washing out your culvert, that may show up in your inspection results as well. In the inspection, you'll also take note of local erosion and pipe damage. These are things that you can easily see and measure, and there's a number of underlying causes for those things. The high velocity may be due to an undersized culvert. The same could be said about a hanging culvert with too much scour downstream. The inlet and outlet configuration could be contributing to this. A long culvert may also be part of the issue. And there may be other design flaws or poor construction. And if you have pipe damage such as corrosion, it may be the soils that you're working in. There's a number of considerations. I'm not going to go into detail about all of these. Of course, fish passage is a big one. Our topic is primarily about fish passage and the repair of culverts for fish passage. But as we try to decide what to do about it, there's quite a few considerations. The geology or the geomorphology is one of those. you might be in a young stream that's actively degrading. There's lots of streams like that up in the Grand Prairie area. So those streams may be lower than they are today. They're eroded down lower 10 years from now compared to today. Your foundations are also a consideration. And bedrock control is something that you would want to know about. Transport and assembly, whatever you decide to do, it has to be constructible. You have to be able to get it to the site and assemble it. End treatments are a pretty common question. End treatments are something you probably would consider on the inlet side of things. Suitable backfill material, we'll talk about that a little bit today. Embankment stability is more of a geotechnical topic. I'm not going to talk about that today. Road geometry. Road geometry is a pretty big consideration. The road geometry governs how much cover you have on top of the pipe and how long your pipe has to be. The width of the road and the amount of cover and the side slopes of the road, they all contribute to the size and length of your culvert. Upstream flooding. Your culvert is probably in a rural area with upstream forest. That's what a lot of the oil and gas areas look like. But if there are other infrastructure upstream of your crossing, you need to design it so that you don't make upstream flooding worse. Channel realignment, a small channel realignment may be necessary to line up your culvert so that you have a reasonably short culvert. Culvert on a skew to the road will be much longer, and it's something that you would normally try to avoid. Overtopping. Overtopping can be a bad thing because it can lead to head cut erosion on the downstream side of the road embankment, and that could wash out your culvert. Overtopping is also a potential asset if you have a location where you can plan for the road to be overtopped. That would reduce your conveyance capacity requirements for your culvert. Buoyant uplift is something we'll talk about today. Blockage from debris and ice. I think this is a really important consideration. When we analyze culverts, we usually analyze it with an empty culvert. The hydraulics are complicated enough without debris and ice, but around here, debris and ice is a big consideration. And future repairs. Sometimes people install larger culverts expecting sometime in the future to install retrofits such as an internal lining because they know the soils are corrosive. And of course, there's so many options nowadays. There's not just round CSP culverts, there are many options. And the problem is actually how to decide. There's almost too many options. So before you decide, before you jump to the conclusion of replacing your culvert, I think we should talk about it first. Because replacing the culvert will probably cost you more than $100,000, even though it's a fairly straightforward earthworks project. So when we start to assess the culvert, what are the key questions? The first one is identifying the key issues. If the hanging culvert is the only key issue, then we can deal with that as the key issue. But the culvert may also be very steep, resulting in a high velocity. So it's important to understand upfront what the key issues are. And then we can look at solving those key issues. Is the culvert damaged? So if the culvert is damaged such that it's threatening the road, then let's go ahead and replace it. Another key question is the culvert big enough, which is something that you can't necessarily see when you're doing your inspection. So it's something we would have to assess off-site. And then there's usually site constraints. are mostly related to the road geometry and how busy the road is. So is the culvert big enough? That's something we normally do in the office, is a desktop exercise. And you need to understand the drainage area contributing to the culvert. You need to understand your design flow for conveyance. You need to understand your fish passage design flow, the channel geometry, and the road geometry. Those are kind of the inputs. Drainage area. Back in the old days, when I first started doing this kind of work, we used paper maps. So we would walk down to the map store and get the right map and come back and lay it on the table and pull out our planimeter, which is the device that I'm showing in the top right-hand corner there. And then we would drag the planimeter around the map, and the display would tell you at the end your drainage area. That was those were the good old days, I suppose. Nowadays we have so many options, and it's so easy to get the right drainage area. I'm showing one of those options where you can trace an area right in Google Earth and get your drainage area. Things have changed a little bit. Conveyance capacity. The traditional method for estimating the amount of flow you need to be able to handle in your culvert is regional hydrology assessment using Water Survey of Canada gauge stations. So you'll look for a nearby river that has gauges on it, and you'll do your statistical analysis on the data and choose a design flow based on that. So a 25-year return period flood would be the minimum that you would look at, and quite often you can design for the 100-year flood without increasing the size of your culvert too much. So the additional cost of the steel is relatively small compared to having to deal with washouts. And I had a boss many years ago who used to go around saying that the 100-year flood happens about every 20 years. So he was half joking but half serious. And we do have big floods. They happen, and they don't always follow the statistical distribution. Alberta Transportation currently has recommendations for conveyance capacity that are a little bit different from what I just explained. So they look at channel capacity, which a lot of us would interpret as the 2-year or bank full flow. Historical high water observations where you have them. There's actually a bridge database with a lot of high water observations for the province. Alberta Transportation maintains that, and they use a basin runoff potential calculation, which should give you similar results to the regional hydrology, but maybe a little bit more consistent. So the basin runoff potential calculation looks a little bit like this. There's a map of the province and different colored areas in the province. The Drumheller, Lethbridge, Medicine Hat area is very dry, has very low runoff potential, although they still have big floods from time to time. So this map shows a 15 millimeter runoff depth potential. 40 millimeters. 40 millimeters, it would be the red area around Edmonton, and those areas tend to have a basin runoff potential of about half a cubic meter per second per square kilometer. So you would multiply that number by the drainage area to get your basin runoff potential. Where a lot of us work along the foothills, you get 80 millimeters of runoff potential, and that results in about 1.1 cubic meters per second per kilometer squared. So there are some options for estimating your conveyance capacity. These are 2 of them. fish passage design discharge. The traditional manner of estimating that was provided by the Fisheries and Oceans Canada, and that was for many years something called the 3Q10, or the 3-day delay discharge with a 10% chance of exceedance. So the basis of that is that you would only want fish to be stopped from migrating upstream 10% of the time, or once every 10 years. And it also assumes that fish are willing to wait a maximum of 3 days before they need to migrate. So that traditional approach has evolved over the years, partly to say that fish are willing to wait longer than 3 days in some cases. So Alberta Transportation has a current standard which is similar to the 2-year flood level. And I want to get this right because it is a little bit different. So their current standard is to allow for about a 20% increase in the average velocity of the channel. That would be in the range of a bank full condition. You would allow your bank full condition would be similar to your 2-year flood on a statistical basis, and you would allow the average velocity to be increased by about 20%. So what does that mean? At the natural channel velocity, there are often some really high velocities in the middle of the channel, but that's not where you find the fish moving upstream. Just like the ducks in this picture, they tend to move upstream along the edges where the velocity is a lot smaller. So if fish, or in this case ducks, are looking for a slower velocity area, roughly half of the average velocity, in a natural channel, they would tend to have about 40% of the channel area in which to swim. A round culvert, if you were to increase the average velocity by about 20%, that area that the fish have to move upstream gets reduced. So it might be reduced from about 40% down to about 20% of the flow area within the culvert. And that's just based on the velocity distributions between that are characteristic between the channel and the culvert. So it gives a bit of a smaller area to swim in, but fish can still get up. Long culverts are an issue for fish. Most culverts are on the order of 20 meters long, and so at 1 meter per second, 20 meters would take about 20 seconds, depending on the type of fish. Salmon and walleye and trout are strong swimmers, and pike are not. So there's different species and different swimming abilities. But long culverts are an issue for all kinds of fish, and I know this is not correct, but I'll say it anyway because I'm not a biologist. Fish are kind of like people. They can sprint for short distances, they can jog for medium distances, or they can walk for long distances. So they are kind of like people in that regard. They can sprint for short distances, but they have athletic limits. So shorter culverts are better, and one of the factors related to the length of the culvert is the road embankment. So the road embankment should be 2 to 1, 2 meters horizontal for every 1 meter vertical drop along the embankment, or flatter. And those are road safety standards. If you're on a highway that will be even flatter, it could be 3 to 1, and in some cases 4 to 1. But most resource roads, I think we build them at 2 to 1. Culvert hydraulics. An outsider, culvert hydraulics are just a number. What's the size? How fast? As practitioners, we often blast through the culvert hydraulics with prepackaged software, but the science behind culvert hydraulics is really complicated. It's perhaps the most complicated analysis you will deal with as an engineer. You have to test inlet versus outlet control. You have energy losses at the entrance and exit. You have tailwater conditions that affect your culvert capacity, but those conditions are not a given like they would be in a university test. It's a simple structure with complex math required to find an appropriate design. Some of the key things to pay attention to are that we want outlet control. Outlet control means that the tailwater controls the flow through the culvert. With tailwater controlling it, we have backwater conditions through the culvert, and the tailwater controls that. Inlet control would be quite a bit different. Inlet control implies that you have supercritical flow or really fast flow. And I don't think we'll get into the difference between supercritical and subcritical here, but we do want the culvert to be outlet control. The way to get that is to keep the slope relatively flat. The flatter the better. There's a lot of guidelines out there that recommend culvert slopes anywhere from 0.5% up to 5%, but I would suggest that you probably cannot pass fish at 5%. So I will always tend to keep the culvert slope as close to zero as possible. And I've had analysts tell me that I can't put it down to zero because at 0% the water will not flow. But that's just not true. The water will flow downhill from one side of the road to the other, even if the culvert is at 0%. So the length of the culvert is also an issue. Talked about that a little bit. Headwater to depth ratio. So on the upper right-hand side, you have some definitions. The headwater is the height of the water at the upstream side, and D is the diameter of your culvert. And the ratio between the two is a design guideline that you'll see in most provinces are recommended to be somewhere less than 2, maybe even 2.5. But I often try, or I usually try, to keep the headwater to depth ratio less than 1. What that means is that the design water level is at or near the top of your culvert. What this does is it allows for some debris accumulation during a flood without overtopping your road. If you use a headwater to depth ratio of 2, that means you need a lot of water stacked up at your inlet to drive your design flow through your culvert. It suggests that your culvert is slightly undersized, and any small bit of debris could result in even higher headwater that overtops your road. So a good practice, I think, is to keep your headwater depth ratio less than 1. Downstream grade control. There's almost always a scour pool downstream of the culvert, even if there's no hanging culvert. And the downstream grade control that's key to your tailwater conditions is about 3 to 4 times the distance, 3 to 4 times your diameter distance downstream. I'll show you what I mean by that. It's a picture of an existing culvert that is not hanging. It's got it's not a hanging culvert. You can sort of see the scour pool downstream of there, and the grade control location is 3 or 4 times the diameter downstream. So that's the diameter of this. I think it's a pipe arch culvert in this case. Time whatever that distance is. If it's 2 meters, then 2 meters times 3 or 4 downstream would be about 8 meters. Downstream is your grade control location. So if the culvert is well sized with similar velocities compared to the natural channel, that the end of that scour pool will be about 3 times the diameter downstream. If your culvert is relatively undersized, the distance to the end of that scour pool could be greater, perhaps 5 times the diameter. It's an indication that your culvert is potentially undersized. I'm not going to spend time on this culvert installation. There's lots of considerations during construction, and these typical details are from the Saskatchewan Ministry of Highways. Of course, we're not in Saskatchewan, but I really like their simple, typical drawings. When we're designing our culvert, we have to understand the different failure mechanisms and guard against them. Overtopping erosion is pretty common. Erosion due to piping through the fill is another one. Piping failure is where water finds a convenient pathway through the fill, through the embankment fill, and scours out a larger opening until all of the water goes through them. Buoyancy failure is, I think, is the cause of a lot of culvert failures and not always recognized as the failure mechanism. And other failure mechanisms include pipe corrosion, which will be fairly easy to spot, and ice issues and issues related to ice and erosion of the foundations. And this is possible for open bottom structures. But buoyancy failure, I think, is one worth showing you because it can be quite dramatic. This is the largest buoyancy failure I've ever seen. It's a 7-meter diameter round culvert in the McGrath area of Alberta, and it failed quite spectacularly. The upstream side of the culvert is shown in the inset. It's standing up like a grain silo because the debris snagged on the inlet of the culvert, even though the culvert was so large, snagged around the inlet of the culvert. The water level is higher than the top of the culvert, but because of the debris, the water level inside the culvert is a lot. It's only maybe half full. The rest of the culvert's full of air, and that air is buoyant, and it causes an uplift force that raises the inlet of the culvert. So the buoyant failure happens at the inlet, and in this case, there was 12 meters of fill material on the culvert, and as soon as the inlet lifted, the culvert became kinked, lost its structural integrity, and then the 12 meters of fill crushed the pipe. There's a few other important bits. If you get into very big culverts, more than 2 meters diameter, you're into multi-plate assembly. That's where culverts come in pieces and you have to assemble them on site. So that it's more labor intensive. And at that point, you might want to consider either multiple culverts or a bridge. You need a certain amount of space between the culverts, and that's required to get the proper compaction of the fill material between the culverts. The road geometry is an issue. The culvert length. A common mistake on the culvert length is that people will size the culvert length such that the toe of the embankment slope coincides with the end of the culvert. So that would be a mistake. It results in a really long unsupported section, and it could expose your culvert to buoyant uplift forces. So the recommended practice is to set the end of the culvert along the embankment slope as shown. Cover depth depends on the traffic and the size of the load on your road. 300 millimeters would be the minimum, and if carrying large loads, you may want more than that. Some of the other topics I won't cover in detail. Erosion protection, there's standard prescriptions for that. The end treatment would be optional, but it helps to protect against buoyancy at the inlet. So the end treatment is something you could consider at the inlet. It improves the hydraulics at the inlet a little bit, but I would say mostly it helps to protect against buoyancy because you won't have the air trapped in an unsupported section of the pipe. Beaver control is pretty tricky and very high maintenance. It's really hard to get that right. And baffles, a lot of the literature talks about baffles in culverts, and I'm not a fan. I haven't had to resort to baffles yet, and I think I'll get through the rest of my career without having to use baffles. Embedment is something I'd like to talk about. An embedded culvert is one that the bottom of the culvert is set down below the grade of the stream bed. This allows natural sediment to fill in the bottom of your culvert so that it appears to be like an open bottom culvert. It's something that can be considered in a lot of places. These pictures are from, I guess it's becoming a fairly old document now, but in British Columbia, they've done a lot of work related to embedded culverts. I have 3 examples for you, and I thought I would have more time than this, but I do have 3 examples for you. The first example is a round pipe. It was a culvert replacement project. The original culvert was undersized and it was a hanging outlet. I'm not showing original before construction pictures. These are all after construction. The outlet is on the left side and the inlet is on the right side. In this case, the culvert that we used to replace the old culvert is relatively oversized. It's oversized for conveyance purposes as a precaution for ice and debris. It's also got an embedded inlet, which allows us to install the culvert at close to zero slope. At close to zero slope, you can't really see it inside the culvert, but the velocity inside the culvert is really low. And then there's an armored outlet. It would have been nice to embed the outlet as well, but space was a constraint here. And I think one of the most impressive things about that culvert is that the amount of disturbance used to install it was so small. There's still trees growing nearby. As a second example, this was a culvert repair. This is not a replacement. There's 2 pipe arch culverts with very little cover on the road. And this is a view from the upstream side. So there is insufficient depth, and at the time it was a high traffic road. That has since changed. And this photo is indicative of normal high spring flow. The solution that we picked here was to install a riffle downstream to remove the hanging culvert condition. So the riffle that was constructed is the first white water you see downstream of the culvert. And all of these other white water sections further downstream are all natural. So the first one is man-made, and the rock on the side is erosion protection. And the area in between is the scour pool. Although it looks like a lot of sediment is accumulated in that area, This was constructed 2 or 3 years ago. I think it might have been 3 years ago. And so it looks like there hasn't been a really large flood since then to scour this out. It also looks like there's maybe a few stones that have moved over the last few years, but it still looks like it's in pretty good condition. Stones will move. You can't expect stones to stay in the same place forever. My last example is similar. It is a different location and riffle constructed downstream to remove the hanging culvert condition. Here's the inlet and there's the riffle outlet. The unique thing about this location was that there was an existing access ramp down the left side here. But on the right side, it was completely unconfined. Water could spill straight downstream or spill to the side towards this overflow culvert. So as part of this riffle design, we installed a containment fill just to keep the water headed in the right direction for the riffle. Of course, you can always build a bridge, and if you build a bridge, that's always most preferred by regulators. And if you build a lot of bridges like West Fraser does, you get good at it. And so the price point between a bridge and a culvert can get small. It can become a small difference. In this case, this bridge was built in the early 2000s and has survived a couple of big floods. Thank you.
Thank you, Michael. That was a great presentation. So we're going to just move on to the Q&A portion. So it's 1:43 right now, and I'm going to cut things off right at the 2 o'clock mark, just to respect everyone's time here. So just so you know in advance, well, actually, before I get into that, I'm just going to throw up a poll here so that we know it's just something we like to do so we get an idea of everybody's affiliations. So yeah, while you're answering that, I'll just give a little bit of details about this Q&A and just answer a question that I've been getting quite a bit. So a lot of people have been asking about where these video recordings would be available and if the presentations themselves would be available as a PowerPoint or a PDF, as well as the Q&A portion. So we are working on making those available on the awccc.ca website. They will hopefully be up soon. But for now, the way that it's working is that once the presenter has finished filling out the Q&A or reviewing the Q&A transcript and entering the answers to the questions that we weren't able to get through during the presentation, those are distributed to all of the attendees of the webinar via email, and a link to the video recording is also provided in those emails. So that's how things are going to work for now. And then as the website is completed and more is able to be provided there, we will make those available publicly. So let's close off this poll. So thanks everyone for answering that. And we'll jump right into the questions. So the first question, to clarify, so I guess this isn't really a question, it's more of a clarification. So on page 12 of the Code of Practice for Watercourse Crossings, it states that Type 1 crossings are allowed on Class A water bodies, only if it is for pedestrians and equestrian purposes. So an existing Type 1 on a Class A can be replaced or repaired. A temporary Type 1 can be installed, or a Type 2 if in conjunction with replacement or maintenance of existing. So I'm not sure if that, yeah, I don't know if you want to comment on that statement, if that was different from.
No, I don't need to comment on that.
Okay. So the next question, how would you make a crossing designed for Q25 work for a Q100 flood? So without significant amount of more steel, as you stated around page 13 or slide 13 of your presentation. So what else do you do to the crossing site to fit this much more water to accommodate for Q100s rather than Q25s for crossings that are already installed to manage Q25s?
That depends on a lot of things, but if your road approach allows for it, you could design a location on the road offset from the culvert where water could overtop it. If you do something like that, then erosion protection on the downstream side of the road is something that you would need to prevent erosion of the road. But if you're already replacing a culvert and you just need to make it a little bit larger, then you might end up sizing it just a little bit bigger.
Okay, thanks. The next question, is there a documentation which details Q25 and Q50 analysis as well as recommended culvert sizing in Alberta? And can this information be shared?
I think the best reference would be the Alberta Transportation website, which has links to a lot of documents. There's similar guidelines in every other province. In BC, you'll find information focused on the 200-year flood, and in Saskatchewan you'll have slightly different information, but more in Saskatchewan that'll be more similar to Alberta. Pretty much every province has guidelines, including fairly detailed guidelines on calculation methods.
All right, thanks. So this one is referring to something specifically on slide 11 of your presentation. So what is the implication of highlighting basin runoff potential out of the three methods under Alberta Transportation? Are there any limitations of using this method?
I think it's one more method in your toolbox. So you still have a number of different ways of triangulating an appropriate design flow. So the regional hydrology is a traditional method. This relatively new runoff basin potential method would be another one. I think the advantages of the runoff potential method is that it's kind of set up for you so that you can't screw it up, as opposed to using a rational method or an SCS method where your choice of curve number might be relatively arbitrary and you end up with a number that doesn't make sense.
All right, thanks. So the next one is referring to slide 16. So are the 5 bullet points referring to the ideal design conditions? So I don't know if you want to go back to slide 16.
Yeah, I'll just go back to slide 16. I don't know which one we're referring to. Oh, culvert hydraulics. I think those are some of the considerations. Yeah, ideally you would have outlet control and a low slope. A higher slope will mean that you have a lot higher velocity. So to pass fish, we need to stay close to zero. The length will depend on your road geometry. But if you cross the road at a right angle and not at a skew, then you have a chance to minimize that length. Otherwise, you would have to start playing games with the road geometry and the road approaches. But most road owners would rather not do that. The headwater depth ratio is that's negotiable. So the using a ratio of 1 is would be ideal, but depending on the situation, you may be forced to do something different.
Okay, thanks. So this one is talking about embedment. It's not really a question, more of a comment, but so this one is saying that for embedment, the understanding was it's about 1/3 of the diameter of the culvert to ensure that native substrate is maintained in the culvert. Can you comment on that?
Yeah, sure. That's a really good question. It depends on the province where you're in. So in BC, they like their culverts embedded 40%, and I think in Manitoba they like it 10%, 10 to 25%, and so because every province is so different, I can get confused about that one. But if you embed it at least 10%, then you're probably going to get some native substrate in the culvert. I don't remember if there's a specific guideline for that in Alberta.
All right. The next question, what about water quality and soil sampling and testing? Are those important factors that should be considered in culvert design?
I don't really understand that question. Soil sampling might help you identify whether you have corrosive soils or not. Although in lots of areas of the province, you probably have a good idea whether you have corrosive soils with or without additional samples.
All right. I'm just seeing some comments coming in about the embedment that we were just talking about. So one came in saying that in 25 years, this person has never embedded more than 20%. Most of the time it is about 10%. And then Mike Hunker from AER made a comment saying it would be good to get clarification on the guidelines for embedding culverts in Alberta.
Agreed.
Yeah, so it'd be good to get some clarification on that, and then we'll make sure to include just some clearer information once we distribute the transcript here. So this next question, in example number 2 of those 3 examples that you were showing at the end, with the constructed riffle, was there consideration given to whether fish can migrate through that cascade?
Yes, there was a quace on site during construction and following construction to provide an opinion as to their ability to pass over that cascade. So you have to remember that the flow during that picture is relatively high flow in the spring. That's the normal high flow.
Okay.
But at first glance, it does look pretty high, doesn't it?
It does, yeah, in that photo. All right, the next question. That was the same question, sorry. So what kind of inspection requirements are there for bridges? Just trying to understand when a bridge should be used over a culvert.
Yeah, that's a whole separate story. There's bridge structural inspections that are required. Culverts don't usually have those kinds of inspections, but bridges do. So there would be additional due diligence by the owner for bridges. And I think if you go to Alberta Transportation, there's more details about that.
Okay, great. Can you elaborate more on baffles and culverts and the rationale for their use and non-use?
Thank you for asking. I forgot to say that the reason I don't like baffles is because they tend to snag debris. And when you start snagging debris, then you end up with a culvert blockage, which could wash out your road. So I would rather not use baffles.
Okay. This one is so this person is at an oil sand area, and there are there's lots of beaver activity in that area. So what kind of mechanism or engineer design can be done to avoid two things? So the first is beaver dens being built in the inlet side of the culverts and accumulation of debris such as branches and other woody debris from beaver activity upstream of the culverts.
Yeah, there's a lot of different products out there related to beaver control at the inlet of culverts. Lots of official kinds of trash vac looking things at the inlet that are pretty hefty and can be bolted on to a head wall or an end treatment. And then there's lots of homemade, very imaginative solutions. There's a really wide variety, and they all sort of work, I would say, and they all sort of do not work. So beavers are persistent little fellows that are going to give you headaches forever.
Okay, thanks. We are running a little.
It's kind of a non-answer, right? But beavers are big challenges.
So we are running close to the end here, so we'll just get to one more question and then we'll close things off. And I just want to remind everybody that if we couldn't get to your question today, it will be included in the transcript, so we will provide answers at a later time. So the next question is, when building riffles, what is the height restrictions involved for fish passage with typical Alberta trout species?
So I usually try to build my riffles with a gradual slope of about 6 to 1, as flat as 10 to 1. The picture shown here is steeper than that. That may be because some of the stones have rolled away. I try to keep the head drop at each one less than half a meter. So if you have a hanging culvert with 2 meters of drop, riffles may not be the right solution for you because you'd need several riffles.
Right, thanks. So we'll just wrap things up. So I'd like to thank today's presenter, Michael Bender. Thank you to everyone who attended the webinar, and we hope that you'll join us for some of the other presentations over the next 5 weeks. So our next webinar in this series will be taking place next Tuesday, May 26th, where we will have Matthew Piper from Fuse Consulting giving a presentation on collaborating with friends, colleagues, and enemies to achieve watercourse crossing goals. So if you enjoyed this webinar, I encourage you to have a look at all other webinars scheduled as part of our series on our GoToWebinar page or on the awccc.ca website, and register for some of those other presentations. So thank you again to Michael for presenting to us today, and I hope to see all of you attending some of our future webinars. Thanks.